So in a recent lesson, I kind of had this idea about this video that I wanted to create, the one that we're doing right now. That would be the importance of mathematics, right? We've already had a video in the past that was why do competition math? It's kind of older, a little monotone, maybe not as exciting, the sound quality, all that stuff. So this could be kind of a continuation of that process, or maybe along with what is mathematics, that video as well. And so I kind of want to discuss this a little bit today and point out what the importance really truly is of math, right? And discussing it not so much in the direct sense of what we're doing with a formula, but what is the application to life beyond that. And so I want to get to that here today. I'm going to go ahead and share screen for starters. And this is where I want to start. And I'm not going to tell you exactly what I'm going with this, where I'm going with this, okay? So it says, do not feed birds or squirrels. See if you can figure it out. Some of you were pretty bright. Let's see if you can see where I'm going with this entire thought process. Do not feed birds or squirrels, right? You might go out sometimes at the park, the nature, right? You're out there, some national park or something. You'll often see signs like this. Sometimes it'll explain why, sometimes it won't. In this case, they decide to explain why. It creates an imbalance in native ecology. It increases their dependence on people for food. What could that have to do with math? Well, let's get a start here. I'm going to give you two different examples here. First, I'm going to show you the difference between the way a typical math student would solve a problem and how what you should be doing if you're an experienced competition math student when you look at things. And so let's go ahead and look. This is an older textbook. I have a copy of it over there in the back shelf. And so this is just the online one that I use when I'm teaching my lessons. And I'm going to start with this formula. And we're going to kind of jump into the middle. I'm not going to develop this formula for you. That's not the point. In a geometric sequence, and I'm going to use a sub 1 because I like it better. With first term a sub 1, okay, and common ratio r. That's what a geometric sequence is. It has a common ratio. So for example, if you look at this one, 3 times negative 4 is negative 12, and negative 12 times negative 4 is 48. That's why negative 4 is the common ratio. You can find it by doing negative 12 over 3. Any term divided by its previous should give the same thing. So you would get 48 over negative 12, negative 4, negative 12 over 3, negative 4. Okay? So let's continue. The nth or general term is given by this formula. I'm going to write it using a. It would be a sub n equals a sub 1 times r to the n minus 1. Okay, now pay attention. I know that some of you already know these concepts, but I want you to understand where I'm going with this so that you can put it all together at the end. So we've got this formula in hand, right? Let's go ahead and scroll down to an example, not example 2, but let's look at how the book is showing people to do it, and without access to a decent teacher, how those students would proceed to work through it. Okay, example 3, find t sub 7 or a sub 7 for the geometric sequence in which t sub 2 is 24 and t sub 5 is 3. Okay, well, let's see what they do. Let's see what the book is going to teach. And I'm going to walk it back and show you what the same exact problem would look like to a competition math student who, again, has been either taught by themselves pretty well or they are well taught. Okay, let's go ahead and scroll down. What do? They say substitute 24. I'm going to go back to the T version, I guess, and I'm going to get confused with the mixture of it. Substitute 24 for T sub 2 and in this formula that they gave us. So let's see what they use. Okay, so we say T sub, the n is 2, so we put 2. We put equals. We go, okay, that must be T sub 1. I don't know what T sub 1 is, so I just put T sub 1 times r, and we know what r is. We don't know what r is. It's going to be to the n minus 1. Keep in mind that this is n, so you'd put 2 minus 1 as your exponent. Now we know what t sub 2 is. As they said, it's 24. They told us it's right there. T sub 2 is 24. So now you could have 24 equals t sub 1 times r to the first. Okay, we can also do that with 25, or with t sub 5 rather. Let's do with t sub 5. You're going to get 3 equals. Okay, so why is it 3? Because it's t sub n, and n is clearly 5. Okay, so you've got 3 equals. It's going to be t sub 1 times, and again, if we look at this formula, it's r to the power of n minus 1. And since n is 5, 5 minus 1 is 4, it would be r to the 4th. Now, if I take this bottom one right here, and I divide this one right here, you're going to get 3 equals t sub 1 times r to the 4th, and you're going to divide the left side and the right side by the upper one. You're going to divide by 24 on this side, and on the right side, you're going to divide by what 24 is equal to, and in that way, we divide by an equal amount on both sides. So 3 over 24, you're going to get 1/8 equals, the t sub 1's cancel, r cubed. Okay, let's see them do this now. All right, we're going to scroll down, we watch, they show this 2 calculations, they solve actually, they do it a little bit different. They solve the first equation for t sub 1. So this one right here, they make it say 24 over r. Now they're going to take this 24 over r and substitute it in. Okay, and we come down here and you see how they solve. They get the same thing, r cubed is 1/8, and then they say r is 1/2. So now what do? Well, we want t sub 7. So of course, we're going to take this formula again, and you're going to go back to the formula to show what it shows you. You're going to let the formula do the work. Okay, let's look. T sub 7, because n is 7, is going to equal t sub 1. And note that we know what t sub 1 is. T sub 1 was 24 over r. And since r is 1/2, that would be 24 divided by 1/2, which is 24 times 2, which is 48. So now we know that t sub 1 is 48. Great. Let's go ahead and put that 48 here, because it's the t sub 1 in the formula right here. And we want times r to, this is n, the 7 is the n, it goes here, 7 minus 1, okay? And you get r to the 6th. So now you have, it's equal to 48 times 1/2 to the 6th power. So 1/2 to the 6th power, 2 to the 6th is 64. So you're going to have this equals 48 times 1 over 64. Now, those are both divisible by 16. You'll go in 3, you'll get 4, you get 3 over 4. Great, we found t sub 7. Now, that's what they do. Let's go down and look real quick just to see. That's their work. Substitute it in, you find t sub 1, you come over here, look at that, 3/4. All right, now let's go back and see how a competition math student, well-trained, would approach this problem. You're just going to look at it and go, what is a geometric sequence? And we're going to stop and ask ourselves a question. We're not going to go, oh, what's the formula? We're going to say, what fundamentally is a geometric sequence? It's something that has a common ratio between the terms. I will multiply one term by that common ratio, and that term by the common ratio, and that term by the common ratio. So when I look at this, I go, well, if I'm at t sub 2, and I want to get to t sub 5, I need 3 common ratios, right? Because t sub 2, if you have any term x, the next term is x times r. The next term is x times r squared. The next term is x times r cubed. So if this x was your t sub 2 and this is t sub 5, then what do? Well, that means that this 24 times r cubed is 3. And you're just going to divide by 24. You're going to go r cubed is 1/8. You're going to say r is 1/2. Immediately, you want t sub 7. You're at t sub 5. How many terms is that? 2. You need 2 more common ratios. 3r squared will be t sub 7, and you know r is 1/2, so it's 3/4 done. Different way of thinking. It's a different way than just go here, use formula, plug in. You don't need to think too much. You don't need to understand. Just plug into the formula. We call that, I call it at least, formulaic thinking. You are reliant on the formula to reason. Oh, I don't know what to do, because you don't actually understand or think about. You're not thinking deeper about the concepts that you're learning. Okay, let's look at how AoPS approaches it. AoPS being the art of problem solving. This is their online text, and I'm just going to come here to it. I purchased this text, as you can see, as part of my ebooks for my account. I also have another copy over here. I'm going to show you something in just for speed purposes. I have multiple copies of this. I also have, the hard copy too from the textbook. So I want to go through the process that I went through in class with a student, okay? And that's for this problem 3.8. There is so much to learn from the textbooks from AoPS. It's not just at face value, though. There is value behind the face value. Let me get to what I mean by that. Just pay attention, okay? So problem 3.8, a convex polygon is a polygon in which every interior angle is less than 180 degrees. A diagonal of a convex polygon, so just make a pentagon, for instance. If I go like this, A, B, C, D, E, then what is meant is that the diagonal is a line segment which connects two non-adjacent. So A, E are adjacent. That's not a diagonal here. That's what they mean by that, okay? Non-adjacent vertices. Part A, part B, part C, part D. What are these questions? How many diagonals does a convex quadrilateral have? How many diagonals does a convex pentagon have? How many diagonals does a convex hexagon have? And finally, question D. Now find a formula for a convex n-gon, or an n-sided polygon, where n is any positive integer greater than 2. Okay, let's go look at what they would do in the solution really quick. Let's see what the question looks like. If I come down here to the solution, these are the example problems, and they do have solutions. But kind of if you look at what AoPS does, they put the gray box in the original text, questions first. On here, they're blue. And they have you figured out the best you can. You see whatever you can do, and then they give the solutions after. And so you scroll down. Let's look at what the question looks like now. When the question is restated, wait, where's part A, B, and C? Why aren't they answering that part? Now, that's the learning behind the face value. What are they actually telling you here? They're telling you that what they wrote up here, this is the real question. This is the thing we're actually asking. The only thing we're trying to actually figure out is what would you do if you were faced with just this question? Just want to know this. I want to know, what is the formula for a convex polygon with n sides? Oh man, that's difficult. How would I think about that? Let's go back and look at the original wording of the problem. This is what you do. This is the thoughts that you need to generate on your own. What does that look like? They're telling you this. This is not going to be on the problems you're actually going to be asked, right? When you get asked these kinds of problems on a competition or something like that, all of these baby steps are going to be left out. Who's going to ask them for you? Is there going to be a teacher over your shoulder that's going to lean over and ask you, how about, why don't you see what happens for a quadrilateral? No, that teacher, that needs to be you. That needs to be you that wants to go and explore this and see, well, you know what? I don't know where to begin. I don't know where to start. So what do I do when I don't know? Oh yeah, the AoPS books taught me I should start asking questions. I should start seeing what happens for basic level cases of this idea. So let's do just that. And I want to show you 2 different ways to get this. There's actually 3 different ways that you can find this formula, okay? Before we go through those 3 ways, well, I'll do 2 of the ways, and I'll come back and show how the 3rd way would be generated. I'm going to go to a whiteboard so that we can talk about this. Okay, and let's just see, kind of follow their footsteps. Let's look at a quadrilateral. Any quadrilateral will do, okay? This is for n equals 4, and we're going to draw the diagonals. From this vertex here, I can draw 1 diagonal. What I'm going to show you right now is the way that I first ever developed how to come up with this formula, okay? How to come up with how to count the diagonals of a polygon. This method is not shown in their text. I do not know of it found anywhere. I think I'm the only one that I've ever seen that created it in this way. Now, what I will grant you is that the way I'm going to show you is not the best way. It's just the way that I first came up with how to count these. It was my own way, okay? So now I'm going to go here, and you're going to get one more, and then you're going to get 0 and 0. It looks like we get two diagonals, okay? Let's look at a pentagon, which is a 5-sided polygon. We're going to get A, B, C, D, and E. Let's count how many there are from A. From A, I can go to D. I can go to C. Oh, I got 2 from A. How many do I get from B? B to E, B to D. I got 2. How about from C? Oh, look, I already have the 1 to A. Let's go down here and go one new one. I only gained one new one, right? And then D already has and E already has. So I get 2 plus 2 plus 1. Over here, I had 1 plus 1. Don't know what our pattern is yet. We can see that the number of diagonals is 5. Okay, and keep in mind, this is for n equals 5. We got 5 diagonals. Let's look at a hexagon. Okay, A, B, C, D, E, F. And from A to E, we have 1, A to D, 2, A to C, 3. We got 3. B to F, 1, B to E, 1, B to D, 1. There's 3. Now C has only 2 new ones, so I put a 2. D only has 1 new one. I've already drawn D to A and D to B when I drew them from B and from A respectively. So then I'm going to have only 1 new way here, and there's no new ways here. So what do I get? 3 plus 3 plus 2 plus 1. Okay, so now we can start analyzing our pattern. If I look, I notice that I always have 2 of the same number in front. It happens to be 3s and 2s and then 1s, and it's going up by 1 every time. What we want to do is compare this to the n value. What is this 2 in comparison to the 5? Well, 5 minus 3 is 2. What about here? 4 minus 3 is 1. What about here? This was n equals 6. 6 minus 3 is 3. It looks like these two values are both 3 less than n. So we could say then that it's n minus 3 plus, and then how would I represent this? This is going to be a series. It looks like it's starting at 1. You're always going to have 1 and 2. This one has 1, 2, and 3. This one only has 1. It looks like you're going to count up to and stop at n minus 3. So you could put it as a block of 1 plus 2 plus ... plus the final one you get to is n minus 3. Now, we can combine this to a more simplified version. I'm not going to completely simplify, but I'm going to get a little bit farther just to clean it up some. This is a series, an arithmetic series. And an arithmetic series, kind of like the other chapter we were doing, if you have the sum of the numbers from 1 to n, I'm not going to fully develop this right now, although we do in the courses that I teach. The arithmetic series sum that I prefer is the average of the first and last times the number of terms. So actually, I will point out one thing about that in a second. If I do n plus 1, which is the first and last sum, divided by 2, that's the average of the first and last. How many terms are there? Well, it's literally counting for you. It's starting at 1, 2, 3. It's counting. So you're just going to put the n. There's n terms. Now, more commonly, if I'm just memorizing the formula, I'm going to think of it as n times n plus 1 over 2. Okay, but if I'm thinking about it as an arithmetic series, I'm going to use the arithmetic series concept of average of first and last times number of terms. I do want to talk about that. Why? You have to ask this question when you're learning. You have to ask when anyone is teaching you, whether it's me, whether it's any other source, whether it's a book. Why? Why does that happen? You want to pick at those kinds of questions. You want to be naturally curious. Don't just be told, oh, it's the average of the first and last. Of course it is. Why? Why is it the average of the first and the last? And so if you kind of explore that idea, you can jump off in different side paths of natural curiosity and exploration. You are intellectually curious when you do things like that. And when you're not intellectually curious, that's not a good place to be. And we're going to talk about that more in a little bit. Let's look at this for an example. I'm going to make another arithmetic series. 3 plus 7 plus 11 plus 15 plus 19. Well, what is the average of these numbers? If you add this, you will get 55. You divide by 5 to get the average, because the average is the sum of all the things divided by the number of things. Okay, what do you get? 11. Interesting. What's the average of the first and last? 3 plus 19 over 2 is 11. What about the second and the second to last? 7 plus 15. What are we using? Gaussian method. Gaussian method was this kind of pairing up of the numbers, first and last, when it's an arithmetic series. And named after Carl Friedrich Gauss. And so you're going to have the 11 in the middle doesn't have something to pair up with. But if these two average to 11, and these two average to 11, and that is 11, this is the same as having 5 11s, right? If I added this all up, and since the average is 11, right, I could say it's the sum of 5 things divided by 5 is 11. The 11 is the average, right? And if I now multiply by 5, 11 times 5, my sum was the product of the average with the number of things. Okay, so then the average of the first and last is equivalent to the average of all the numbers. Okay, I didn't fully prove that to you now. I'm not going to go ahead and do that. We could using something like a sub 1, a sub 1 plus d, a sub 1 plus 2d as our terms, and keep going and try to establish it. I'm not going to go into that level right now. Okay, I just want to cover at least that you understand why that formula works. In the course, we may or may not do that when we work through it. You will do it. It's just a matter of whether we'll cover that part of it in class or not. Okay, so now let's do that with this one. In this formula, we stopped at n. In this formula, we're stopping at n minus 3. That must mean, rules of math, I should be able to plug n minus 3 into these n's and get a sum for this bracketed value here. It must be that this part is n minus 3 times n minus 3 plus 1 over 2. Oh, wait. Yeah, n minus 3 plus 1 over 2. Why? Again, all we're doing is replacing this n and this n with n minus 3s. Now they're here and here, okay? And then the plus 1 and the over 2, they're still there. They didn't go anywhere, okay? We did put the n in a parenthesis now, so we understand it's the whole binomial and not just one thing anymore. Okay, so now what? That's what I came up with. This is my formula, okay? Now, that would be simplified one more time, get a little bit farther. It is equal to n minus 3 times n minus 2 over 2. And so that's just this part, just the bracket, okay? What about this n minus 3? So now we have that it's n minus 3 plus n minus 3 times n minus 2 over 2. That's where I'm going to leave it for now. Now let's look at several other ways of doing it. The two ways that the art of problem solving are going to give you. Try to remember what this is. I'll take a screenshot. Maybe I'll come back and find it later. Okay, I'm going to clear screen. Let's go through it a different way now. And to be honest, like I said, these ways are going to end up being superior. One of the ways that you can do is if we go back to the text and look at an earlier problem, this round robin tennis tournament 3.7. They first, by the way, had you do it in 3.5, where you did a round robin tennis tournament with 8 people. And now they're having you do it with n people. Does that seem familiar? It's exactly what they're doing collectively in 3.8. They're doing a specific example to let you understand the generic example. What do you have here? You have a roadmap for how to create these kinds of ideas on your own. You try to find specific examples, and then you try to extrapolate to the general so that you can understand in general what's happening and prove it for all such cases, not just the case when there's 8. And so if you look at the case when there's 8, the way that you can think about it is of the 8 people, it's a round robin tournament, all 8 people play everyone else. And again, there's a lot of depth you can go to in this problem. I'm skipping over some of it for the purpose of what we're doing. You could say those 8 people if you're one of those 8 people, okay, A, B, C, D, E, F, G, H, there's 8 people. Okay, let's say you're person A. How many people can you choose from to play? 7. So you could take any of the original 8 people, choose that person, now choose their opponent, 7 choices. Does that mean there's 56 matches? No, because we counted A as the first choice, B as their opponent. We also counted B as the first choice, A as their opponent. And so this whole chapter, this whole section, chapter is about correcting for overcounting. So how do we get rid of this overcounting? Well, for every case that we found, we actually counted it twice. So we're just going to divide by 2. Okay, now we're going to take that same thought, and that's why this, by the way, for n people is n times n minus 1 over 2. Okay, we're going to use that same thought on these convex polygons. Let's go forward and back to the whiteboard. And let's say that we have back to this quadrilateral, okay, A, B, C, D. If I want to connect a diagonal of A, let's say I chose an A as my first choice. A diagonal is a line segment, right? So it has to connect 2 points. Well, how many choices do I have? I can first choose from my 4 points. I can choose a second point. So B, C, or D. How many choices do I have? 3. I do 4 times 3. But again, we've counted all of them twice, so we will divide that by 2. Then that's going to find all the segments that you could possibly connect. So now at this point, what do? Well, why does this not give what we got earlier? Earlier we got 2. Now we're getting this. Oh, because this counts all connections between points. You can think of it almost like 4 points instead. We start with which point do I choose first? Now I choose its connecting point, dividing by 2. Kind of like choose player A, choose their opponent. We counted that match twice. We divide by 2. Same thing is happening here. We've counted A to B and B to A. So we've got that, but we still need to get down to 2. And the reason is because not all of these are diagonals. So we have to subtract 4. So if we do the same thing with n instead, it would be n times n minus 1 over 2 minus each of the sides. Well, don't we have to count the sides twice? Because didn't we count it? No, that's taken care of with this division of 2. We just need to subtract that 1 counting now that we've been left with. Okay, we subtract that 1 counting, and now what will you get? 12 over 2 is 6. 6 minus 4 is 2. Okay, great. So now we've found 2 ways. Let's look at a third way, which is really, in my opinion, the most efficient method and the best method to think about this. Let's look at this from another third viewpoint, if we will. So you have this. Instead of thinking about it as the way I did, I mean, obviously you get 1 here and you get 1 here. Rather than stopping and putting 0 new diagonals here, why don't we just choose to say there's 1 diagonal from C? It's true. And there's 1 diagonal from D. In fact, all 4 of them could be said to have 1 diagonal emanating from their vertex. Okay, but then how would we get back to 2? Well, if I just did all of the vertices, how many vertices are there? N. What does 1 represent in relation to n? N was 4, 1 is 3 less. It would be that we subtract 3 still, n minus 3. Okay, so then we divide that by 2. What's the n minus 3? It's this 1. Now here's the kicker. You need to ask, again, don't accept. Don't just go the pattern. The pattern is 1 is 3 less than 4. Great, thank you. Ask why. Conceptually, go beyond the numerical value. The conceptual part is the following. If you're at A, where can you not go to make a diagonal, which cannot be a side? You cannot go to A itself, and you cannot go to D, and you cannot go to B, the neighbors of A. How many points did we just lose? We lost 3. That's why we subtract those 3 values. Is it different for a pentagon? Let's go look. If we look at a pentagon, what do we see? We have A, B, C, D, E. How many diagonals can I draw from vertex A? A to D, A to C, you get 2. What about B? B to E, B to D, you get 2. Now, instead of doing my method, let's go, well, C also has 2. 1 to A, 1 to E. D also has 2. E also has 2. They all have 2, just like these all had 1. Here, n is 5. It's a 5-sided figure, and all of the values we're getting are 2. So is 2 always 3 less than 5? It is. Why 3 less? Confirm it again. Keep asking. Keep reinforcing the underlying concept. It's the concept that you're trying to understand. It's the thinking process, not just a formula. That's what's critical to understand here. You get rid of A because A cannot connect to itself. A cannot connect to E. A cannot connect to B. That's 3 lost points. How many can it connect with? Only C and D. Those are the only diagonals you can create from A. So it's a choice first. Which point am I going to start at? I have 5 choices. That's my N. Then I say, how many points can I connect to that will count as a diagonal? I can connect to N minus 3, minus my original point, minus its neighbors. Pause and ask, is this true for all convex n-gons? Yes. Okay, it's true for all of them because no matter what you do, every vertex will have a paired out side like this. So you're going to lose the vertex you're at, you're going to lose the vertex that's your neighbor, whatever it is, and the other neighbor over here. And they will all have 2 neighbors like this, okay, to make the outside of the polygon. So then we know, why are we dividing by 2? Because we counted it twice. We counted from A to C, we counted from C to A, we're correcting for that overcounting, we get 2. So now what? Now we have 3 different formulas. Let's write all of them here. The best of which, honestly, is this one. In my opinion, I mean, obviously, some people might differ, okay? So n times n minus 3 over 2. Let's first look at my calculation. I had n minus 3 plus n minus 3 times n minus 2 over 2. Pretty sure that's what it was. How is these the same? They must be the same. Do you just go, oh, well, they must be the same, so I'm just going to accept that? Stop, prove, establish, right? Make sure that you're verifying these thoughts that you have. Don't sit at the assumption they must be the same. I'm going to move on to the next question. Why would you do that? Why would you move on to the next question? The answer? My goal with homework is to get my homework done. Does that sound like you? Bad place to be. Your goal with the homework, especially in competition math, is not to get the homework done. That's not the purpose. That's a side effect of learning. The purpose of education is to learn, okay? So to learn how to think. That's your goal. That's your purpose. Now, a side effect of that is that your homework gets completed. And why would you want the homework completed? Oftentimes it's so that you can go indulge in self-satisfaction, video game, TV show, social media, text with friends, right? Whatever it might be that you want to go do, maybe that's preventing you from making growth in yourself, okay? So then you go over here, you do 2 over 2. Now what? Why did I make it 2 over 2 so they have the same denominator? Let's factor out the n minus 3, because they both expressions have it, and the 2. If I factor out n minus 3 over 2, what's left? Okay, I still have this 2, and I have this. I have 2 plus n minus 2. Stop and make sure you see where that's coming from. I'll put it in red. This 2 is left behind. I'm factoring out the other part of it, and this n minus 2 is left behind. This plus sign is left behind. The other part is what we're factoring out. So now 2 plus n minus 2, the 2's cancel. Are these formulas the same or are they different? They are the same. Let's look at another one. Let's look at the other one that we created too with the other formula, because all 3 of them must be equivalent. Okay, so we have n times n minus 1 over 2 and then minus n. How could this be the same? Let's put a 2 here and a 2 here. All right, so then in this version, I can factor out n over 2. Let's circle all of that in black. This is coming out, this is coming out, this is coming out, this is coming out. What's left? What's left we'll put in blue. We have n minus 1, we have a minus sign, we have 2. We have n minus 1 minus 2. That's what's left. the n over 2 outside. What is that? N minus 3. What are they all equivalent? 3 different ways to think about it. 2 of which you can find in AoPS, one of which I showed you as well. You want to make yourself into someone who asks the questions, who explores. If you don't even want to explore, you're probably not going to ever qualify for the AIME. Okay, and this is where I wanted to get to. Let's get to my final point of this video. Why does this matter? Are we doing the competitions are we doing math so we can win an award, so we can get a 4.0 or 5.0 if your school has that scale system, so that we can get into the university that we want to get into? Is that the purpose? The purpose so we can get a pat on the back? Good job, you made the AIME. Why are we doing all of this? Why does math matter? It's not because of the face value. Math is a sandbox. It's a sandbox where you can explore and it's safe. Why is it safe? Because we have definitive outcomes. We have deterministic values. We can determine what the truth of a matter is. It's math. That's what's great about it. Why would that be important? Why is that skill important? Because you can have assumptions about how I think about something. I can verify if my assumptions were actually valid. I can know at the end of the day, did these things work out? Did my method work the same way as their method, the same way as their second method? Was it or was it not? We know, we can tell. What would you do with such a skill? Let's go back and look at this thing again. We go back to this screen, and we come back to this, do not feed the birds or the squirrels. It creates an imbalance in native ecology. It increases their dependence on people for food. Well, I've got one. How about some food for thought? Let's go look at another one. This is from the National Park Service. And it says, I didn't know that. Don't feed wildlife. There's a whole thing. Look, cute squirrels. I love squirrels as a kid, by the way. They are really cute. You can read all about it here. And so it talks about it here. It says, depending on humans for food is called food conditioning. This is a thing in nature. Food conditioning is dangerous for animals because it can lead to serious consequences like getting sick, starving, or even having to be killed if they become too aggressive. Animals lose their fear of people when they get used to food. They may beg, steal, or rip into your backpack or tent, and so on. And now let's go look at one other thing they mentioned down below. I'm not sure where it says it there. If you look down here in this chart they make, they explain something else too, right here. There are risks to wildlife when you feed them. Animals that rely on human foods can stop hunting or foraging and starve. They will starve because they became dependent on you or other humans for their food. If humans stop feeding them, they're not able to survive. What happens to you when you outsource all of your thinking to other people? What happens to you when you are dependent upon other people to think for you? The purpose of the math that we're doing is not to plug into a formula. The purpose is to expand, to learn how to think for yourself. That's why when you look at the AoPS version, there's a different way of wording the original problem versus how it's worded when they word the solution. They're showing you something. They're showing you how to think. Teaching is not, the best teaching is not telling you what is true. It's helping you learn to think about what is true for yourself. And as you go through life, you're going to learn about a great many things. There's going to be a great many people and sources of information. They're all going to be vying to be claiming to be true. You're going to have it from, let's say, religious leaders. You're going to have it from politicians of all stripes. You're going to have it from governments of all stripes. You're going to have it from news media of all stripes. You're going to have it from teachers of your world. They're all going to be trying to tell you what they want you to believe is true. Are you going to be like the squirrels? Are you going to become dependent on other people? You're going to be starving for actual truth, because you're dependent on someone else to think for you. Think about what a weak position that puts you in. Just like the squirrels, just like the birds. This is why math matters. This is the importance of math. It's a sandbox where you get to practice thinking, because when you go out beyond it, math is not about the formulas. Math is about the processes that you're developing. It's the processes in thinking. It's the development of thought. It's like the scientific method. I have a theory. I think I can do this. Now I can prove I can do this. But rather than it be within the scientific laboratory where we're mixing chemicals or various other things, we do it in paper. We do it with thought. And in this way, you learn to think rationally and logically and creatively. And you're not dependent on networks or teachers, even me. You're not dependent on me. You're not dependent on a textbook to learn. We can go back. We can learn to teach ourselves. We can learn to discover what is true. That is what we want. And that's what the AMC is doing as well. It is measuring oftentimes your ability to teach yourself on the fly in the moment. That's why the test upgrades every year. They're advancing it. It's not a test based on memorization. The real measurement is the people who can react in live time under the pressure of time and overcome an inadequacy. I can teach myself in this problem. You don't look at it and go, I didn't learn the formula. You're a robot. Don't be a robot. Don't be an NPC. Learn to think for yourself. That's what math is really all about. And that's why it's a core fundamental idea in any well-rounded education. So when you do math, when you do these contests, don't think about just the awards. Don't think about the accomplishments. Think about you're creating yourself, your future self, someone who can function in a society that's going to be trying to convince you of various things, some true and some false. You need to be one who can evaluate those. That's why math matters. That's all I got for you today. I hope you enjoyed this. I'm going to stop recording at this point. This is what my classes are like. If you have any questions, leave them in the comments below. I will respond. You can go to my website if you would like to sign up for the classes as well. Thank you and have a good one.